What we're going to think about now is if we given some triangle, and here we have triangle ABC, what are the medians of the triangle and how do they relate to each other, and do they have some interesting properties? And you might guess that they do. So the median is if we start at one of the vertices, so let's start at this one right over here, and then we bisect the opposite side. So this right over here would be a median. And so it started there and it bisects this side right over here. So the length from B to, let's call this D, is equal to the length from D to C. Now let's do that with every side. So I can draw a median over here like that. So, and let's call this point E. So the length from A to E is going to be equal to the length from E to C. Although I kind of drew it a little lopsided, but that gets it pretty close. And then we're going to draw another median. And I'm not going to prove it in this video, but all of the medians, and this is another neat thing, that when you have three lines that will always intersect at one point, but all the medians do intersect at one point. They all are concurrent. They all hit one common point in the center. So let's draw it that way. I'm not going to prove it in this video. So this length, let's call this point right over here F. So this length right over here, this length right over there, is equal to that length over there. And the point at which these medians intersect is called the centroid. The centroid. And when we start studying physics, if this was a uniform triangle and you were to throw it, it would rotate around the centroid right over here. But we'll just study it geometrically for now. So let's call the centroid, well, we've already gone up to F, so let's call the centroid G right over there. Now, what I want to, that by itself is neat, that you have a centroid, that if you were to throw it, if it was a uniform mass, that it would rotate around the centroid. But what's even neater about this is that we can see that we've divided this triangle into 6 smaller triangles. What's really cool, even though these aren't congruent triangles necessarily, but they do have the same area. And that's what we're going to prove in this video, that these 6 triangles all have the same area. Now, to start off, I'm just going to look at different pairs of triangles. So let's look at these 2 triangles right over here. Let's look at those 2 triangles over here. And to show that those 2 have the same area, we're just going to invoke a very simple principle. So imagine rotating just those 2 triangles over. So just rotating just those 2 triangles over, it would look something like this. It would look something like this. Let me try my best to draw it, where this would be point G. I'll even try to color code it the same. That is point G. That is that side right over there. This is point C. This is point B. That is point B. And then this right over here would be the second part of that median right over there. That over there would be point D. Now we know, and I didn't draw it actually that nicely over here, we know that this length is equal to this length right over here. That these 2 triangles, if we're starting to think about the area, they have the same base. And we know area is equal to 1/2 base times height. So they definitely have the same base. What about their heights? Well, they also have the same heights. Both of their height is exactly that tall. They both have the same height. So both of them have the same base. They both have the same height. On an obtuse triangle right here, the altitude sits outside of it, so that might be a little counterintuitive. So if you have an obtuse triangle like that, I say obtuse because this is more than 90 degrees. Your altitude, your height, will actually sit outside of the triangle, but that's okay. Both of these triangles have the same base and the same height, so they must have the same area. So if this one right here has area x, this one right here will have area x as well. And you can use the exact same logic to say, well, look, this guy and this guy, they have the same base, and they both have the same height. So if this one right over here is of area y, then this one over here is also going to be of area y. They're going to have the same area. And then finally, we could do the same thing for these 2 characters up here. They both have the same base. This was BF is equal to FA. And they both have the same height. We drop an altitude like that. And so if we call this area, right over here Z, you could call that area Z as well. So far we've shown that we can divide this into 3 pairs of triangles that have the same area, but we want to now show that they all have the same area. And to do that, we can invoke this same principle, but we'll do it with different sets of triangles. So now let's look at triangle BAE. Look at triangle BAE. Triangle BAE. So the area of triangle BAE, is going to be equal to z plus z plus y. Z plus z plus y. And let's look at the area of triangle BEC. BEC right over there. That's going to be, this triangle right over here is going to be x plus y. So the area of BEC is going to be x plus y. But the same principle. They both have the same base, and they both have the same height. We could drop an altitude like this. This one is obtuse so that the altitude sits outside of it, but they have the exact same height. So these two areas need to be equal to each other. So you have z, well, let me just add that up. That you have 2z plus y is going to be equal to 2x plus y. 2x plus y. Subtract y from both sides, you get 2z is equal to 2x. Divide both sides by 2, you get z is equal to x. And so we could say, we could write an x here and an x there. So we know that all of these four have the same area, but we still have to worry about these y's here. And to do that, we just have to kind of rotate the way that we look at it. And now look at triangle ADC. Let me do that in a different color. Triangle ADC, which I'm highlighting right over here. Triangle ADC, whose area, so the area of ADC is going to be 2y plus x is equal to 2y plus x. And then look at triangle. Let's see, what color have I not used yet? Let me use this green. Triangle ADB. Triangle ADB. Triangle area of triangle ADB is going to be equal to, well, you could say it's 2z plus x, but we know that the z's are equal to x, so it's really just x plus x plus x. It's really equal to, ADB is equal to 3x. And we have the same idea here. ADB has this base, which is the same as ADC's base, and they both have the same height. We could drop an altitude like this. They have the same height. We're just invoking this principle over and over and over again. So these things have to equal each other. So we get 2y plus x is equal to 3x. Subtract x from both sides. You get 2y is equal to 2x, or y is equal to x. So that's a really neat result. You go from each of the vertices of a triangle to the opposite side, and you bisect that opposite side, and you do that 3 times. You have 3 medians. These lines are called medians, where they intersect as a centroid. And what's really cool is it divides the triangle into 6 smaller triangles of equal area.